Hello and welcome to a supplemental video in Phys 1104, and this video is relevant both to the momentum unit of the course and to the principle of relativity unit of the course. I think it's going to be most helpful to you as you're preparing for various experiments in the course where you're studying cart collisions. So that is basically the momentum unit. But the data I'm going to use here is data that I introduced during the principle of relativity unit, and so I'll make some comments that are relevant to that unit. In lecture 2 of the principle of relativity, I showed some of this data, and I showed it in rather little detail because, of course, in that video I was concentrating on the physical principles and I did not want to get bogged down in the details of the data analysis. But now it's going to be useful for you to see how I carried out the data analysis. So the decision I made for that original video was that I would simply state things to 2 sig figs. And to 2 sig figs, there was good agreement. So what do I mean? I mean I was checking, in this case, conservation of momentum, and I was doing it by comparing the ratio of inertias and the ratio of the delta v's, and they both, to 2 sig figs, came out to 1.8. Now, in fact, my data was good arguably to 3 sig figs, and so let's look at what happens then. As I usually do in the video lectures, I got my data from video analysis and then have plugged it into a spreadsheet to carry out the analysis. In the lab, you'll be using Data Studio, and that'll make certain aspects of this a little different, but by and large, the way you're going to go about it is the same. It's just the details of how you do it that'll be different. So I've got my data, and I'll just show you the graph, which you've seen before, of the velocity versus time. And I'll just point out that the reason I've got things highlighted in yellow here is to tell me that this part is the before collision part that I'm using to compute, say, averages mean of the velocity. And here's the part after. And in here, this is where all the messy stuff is happening during the collision, and I don't really want to use that because that's complicated. So it's good when you're working with data to give yourself some indicators of what you've used, because you'll probably have to keep selecting that set of cells over and over again. You can speed things up. So I've calculated mean velocities for the 2 carts before and after the collision, and here they are. I've also calculated SDOMs. So I also have the measurements of the inertias, and this is actually, this MB is to 3 sig figs, but the spreadsheet won't show that. So really, when I divide those by each other to get the ratio of inertias, I should quote 3 sig figs, and so it should be 1.81. And similarly, I believe from my analysis that I have 3 sig figs for my velocities, or at least for my change in velocities, and so I should really quote 3 sig figs for dvb by dva, and so that comes out to 1.78. So it's not quite agreement, it's fairly close, but you don't really know how to compute an uncertainty in a ratio like this. And so what we'll do now is see how working with the momentum before, the total system momentum before and the total system momentum after, you can work out the uncertainties and make better decisions about whether momentum was conserved. Here, down here near the bottom of the screen, with the cell references highlighted in different colors, is where I calculated the initial system momentum, and you can see the cells I calculated it from, and so you can see it is just an MA VA plus MB VB, like you would expect, and then I did the same thing for the post-collision to get the final momentum. And look, they don't quite match, do they? But of course, you know, this is experiment. We don't expect them to come out exactly the same. There's uncertainty. Well, how do we calculate this uncertainty? You can see I did calculate the uncertainty over here, but how did I do it? You know how to get an uncertainty when you've got multiple measurements of something. You just take an SDOM. But what about when you've got a quantity you're calculating from some other quantity that has uncertainty? So this is a particularly simple case that we're looking at here. Let's say we're getting the uncertainty in the momentum of a single cart. Well, that quantity is calculated just as an inertia times a velocity component. And let's suppose that the uncertainty in the inertia is small enough that we can just say we can ignore it. And then the velocity component has an uncertainty, right? This is an S-DOM sigma v bar x, right? That's how we write an S-DOM. Then the momentum that you would quote can be thought of as that inertia times the mean plus or minus S-DOM, right? Our best estimate plus or minus our uncertainty in the velocity. And so just multiply that through and you get mvx bar, so there is our mean or best estimate of the momentum, plus or minus now m times the uncertainty in vx, and so there is our uncertainty in px. And then what we actually need is a system momentum, so we now need to add the momentums of two different carts. So I'm just going to say we need an addition rule if we have any old quantities a and b with uncertainties sigma a bar and sigma b bar. Then it's not totally wrong to say that the uncertainty in the sum, a plus b, is just the sum of those two uncertainties. And I say it's not totally wrong because some of you will go on and take a stats course and learn to do it properly. This rule, if you can call it a rule, actually somewhat overestimates the uncertainty. That is more or less how I got these uncertainties in the momentums, and if you now compare the difference in these momentums and those uncertainties, you can actually see that we don't really have good agreement. So does this mean momentum wasn't conserved in the collision? Well, not so fast. There was friction, right? This is carts, so the friction is small. It's an approximately isolated system, but it's not quite isolated, and so we should try and account for that. So all I've done is I've taken some of the Vx versus t data, and I've just taken the post-collision data because I want a nice flat bit, not during the collision, where all that the cart should be experiencing is friction. And now I've just taken best fit lines to estimate the accelerations of the two carts. And so there we go. I've got the accelerations of the two carts, and now I can find the rate at which the system momentum is changing, right? I can figure out, I could figure out the momentum at one time and then apply that acceleration and figure it out at another time, or what in fact I've done is I've said it is the inertia of one cart times its acceleration that I just read off my best fit line, plus the inertia of the other cart times its acceleration, which I again just read off the best fit line, and that gives me a rate of change in the system momentum. And now I can say, well, okay, so my initial momentum around the middle of the times that I used to calculate that would be about 0.3 seconds. So I'm going to say that's an estimate of the momentum of the system at that time, 0.3 seconds. And then again, for after, that's an estimate for around about 0.9, 0.93-ish seconds. And this is all going to be very rough anyway. And so all I have to do now is say, well, I know my rate of change of momentum. If I now just multiply it by about 0.6 seconds, I'll get my expected change in the momentum of the system that would have happened if only friction were acting. And in fact, I see a larger change due to friction, or an expected change due to friction, than the actual change I observed. And so that lets me conclude that it certainly doesn't look like the collision caused any loss in momentum, because the change in momentum I see is, in fact, less than I would expect just from friction. So later on in Lecture 2 of the Principle of Relativity unit, I showed you this data. If you have only watched the momentum unit and don't know what I mean by earth frame and moving frame, don't worry. Just focus on the earth frame. So in that video, I claimed that there was good agreement between the initial and final kinetic energy of the system. It was 0.4 joules. And as you'll see, as I show you the real data, I was actually telling a slight fib there. However, I will show you that I wasn't telling a serious fib, because the main claim I was making was that there was agreement between the Earth frame results and the moving frame results, and in fact there was good agreement. It just wasn't quite as simple as I claimed it was. So here near the bottom of the screen, you can see my calculation of the initial kinetic energy of the system, and you can see I'm using again the inertias of both carts and the mean x components of the velocities of both carts, and I did the same thing for the final. And notice again, they don't quite match, and there's a delta k that I calculated there, and again, it's not quite consistent with 0. Now I'll note, I calculated uncertainties in all of these. In the lab where you do this, I do not ask you to calculate an uncertainty in the kinetic energy because you don't know how. But nevertheless, let's talk about the fact that I see a slight change in k. Well, again, there's friction going on, right? So this system is close to closed, but because there's a little bit of friction, there will be a little bit of the system's kinetic energy being converted into thermal energy in the environment. And so we don't actually expect to see perfect conservation of energy. And so, although I don't ask you to do this in the lab, I have, again, found by actually plotting the kinetic energy versus time in my spreadsheet, and then getting a slope off of it, I've found the rate of change of the kinetic energy in my system, and this is, again, post-collision, so this has to be just from friction. And so I can again get a rate of change somewhere over here, a rate of change in my kinetic energy, which I just read off of that best fit curve. And again, I can multiply that by about 0.6 seconds and get the expected change in the kinetic energy, and it's about 8.4 millijoules, and the actual change in kinetic energy I see is about 7.2 millijoules. And so I can again conclude that the loss in kinetic energy I see in this system is just due to the friction, not because of anything happening in the collision. And so this looks like an awfully elastic collision. Like I said, I slightly fibbed in the original video lecture where I was using this and talking about the agreement between the different reference frames, but it was only a little white lie, because one thing to notice is here is my delta k, and this was in the Earth frame, and if I go over to the spreadsheet where I did all the analysis for the moving frame, I get a delta k that is almost exactly the same. So while the kinetic energy was not conserved, the claim that the two frames are agreeing about delta k is true. The remaining thing I just want to mention is a difference between what I'm seeing doing the analysis the way I did versus what you'll see doing it in Data Studio. And in fact, the pre-lab of the first of the two collision labs gets you to think about this. So here's a big hint about that pre-lab. So here is data on a cart collision, and what was happening here was that a low inertia cart, I think it was a single cart, was coming along to the right, and this is the V versus T data, and so you can see this positive Vx, and then the collision occurs, and you can see afterwards the other cart apparently has a negative Vx. But does that make sense? You know, let's say cart A was moving to the right, it collides with cart B. Should cart B be then moving to the left? What's going on here? That doesn't make any sense. Well, remember that you are doing this with two motion sensors. One motion sensor getting the data on one cart and the other motion sensor getting the data on the other cart. And so one of the motion sensors has to be looking from one end of the track, and the other motion sensor has to be looking from the other end of the track. And that explains why this may not look quite the way you would expect.